This video discusses the least squares method for estimating the parameters of a regression equation. So the least squares principle works off of the idea that we're trying to use the data to position a line that best represents the relationship between our two variables. And so what you do is you make a scatter diagram to visually position the line and then use your judgment to make that best line. But if we look at the image in the lower left-hand corner, that graph has four different people using their judgment to draw the line. And so we have a method called the least squares method that gives us a single best regression line that we see in the top picture here. So the slope of your regression line will be the standard deviation of your y values divided by the standard deviation of your x values multiplied by your correlation coefficient. And if you remember, your correlation coefficient is the sum of your x observations minus x bar times your y observations minus y bar divided by n minus 1 times your standard deviation of x multiplied by your standard deviation of y. And then the y-intercept is going to be the average of your y values minus the slope multiplied by the average of your x values. The general form of the linear regression line is the same as the equation of any line. So in the formula, beta naught is the value of y hat when x equals 0, and beta 1 shows the amount of change in y hat for a change in 1 unit of x. A positive value for beta 1 will reflect a direct relationship between the two variables, and a negative value will indicate an inverse relationship. So let's look at the least square method a little bit differently. To illustrate the least squares method, suppose the data were collected from a sample of 10 Butler Trucking Company driving assignments that we have shown here on the right. And we're looking at, for an individual observation, or called the ith observation, in the sample, x sub I would be the miles traveled and y sub I is the travel time in hours. And so the values of x sub I and y sub I for 10 driving assignments in the sample are summarized in the table on the right here. The chart on the left is going to be a scatter diagram of the data that we see on the right. And so we have miles traveled shown on our horizontal axis, and travel time in hours is shown on our vertical axis. Longer travel times do appear to coincide with more miles traveled. The relationship between the travel time and miles traveled appears to be approximated by a straight line, which here would be a positive linear relationship being indicated between our x and y values. Therefore, the simple linear regression model is chosen to represent this relationship. So if we look at the least squares method, basically we're just trying to minimize our error. Okay, so when we're looking at this formula, the things that you need to know is that y sub I is your observed value for the dependent variable for a specific observation, and then y hat sub I is going to be the predicted value of the dependent variable of a specific observation, with n equaling our total number of observations. And so when we look at our residual for an individual observation, that's going to be the error made using that regression model to estimate the mean value of that dependent variable for that specific observation. And so when we look at the error for an individual observation, we see that as E sub I equals Y sub I minus Y hat sub I. So basically what you're doing is you're looking at the actual observation minus your predicted observation. And so basically what we're looking at is minimizing our sum of squared errors. And so if we go back to our trucking company data, we have an estimated slope of 0.0678 with a y-intercept of 1.2739 to give us our estimated simple linear regression model of y hat equals 1.2739 plus 0.0678 times x1. And so we would interpret this line with B1 and B0 as we would any other y-intercept and slope of a straight line. So B1 says if the length of a driving assignment were 1 unit or 1 mile longer, the mean travel time for that driving assignment would be 0.0678 units longer, or basically approximately 4 minutes longer. And then the interpretation of B naught would be if the driving distance for a driving assignment was 0 units or 0 miles, the mean travel time would still be 1.2739 hours, which is about 76 minutes. With the least squared model, because we have no empirical evidence that the relationship we have found holds true for our values of x outside of the range of the values of x in the data that we use to estimate the relationship, it's very risky to use extrapolation and should be avoided if possible. So if we're looking at our Butler trucking example, this means that any prediction outside the travel time for a driving distance less than 50 miles or greater than 100 miles is not going to be a reliable estimate. And so for this model, the estimate of beta naught is going to be meaningless because that's going to be the case in which y is 0, and that's outside of our range. But if the experimental region for the regression problem includes 0, the y-intercept might have a more meaningful interpretation. So here we're looking at the simple linear regression model and compares using that model to predict what we would have for 100 miles traveled, and we have a predicted value of 8.0539, and we subtracted the actual time for 100 miles on that first driving assignment. So we do 9.3 minus our predicted value of 8.0539 to get an error of 1.2461. And so that's just the error for that very first driving assignment on this chart. But now, if we go through and we calculate that value for each of our observations, we can put that in the title, in the table that you see here in the lower left-hand corner. Some things I want you to notice about this figure is that the sum of the predicted values for the y hat is equal to the sum of the values of the dependent variable y. Also, the sum of the residuals e sub I will be 0, and the sum of the squared residuals e sub I squared has been minimized. Now here we have a graph that shows a simple linear regression of the line y hat equals 1.2739 plus 0.0678 x sub I superimposed on top of our scatter chart for the Butler Trucking Company data. So this figure will also highlight the residuals for driving assignments 3 and driving assignment 5. And it shows that the regression model underpredicts the travel time for some of the driving assignments, such as driving assignment 3, and overpredicts our travel time for others, such as driving assignment number 5. But in general, this line does appear to fit our data relatively well. In our last figure, we have a vertical line drawn from each point on the scatter chart to the linear regression line. And each of these lines will represent the difference between the actual driving time and the driving time to be predicted using the linear regression for one of the assignments in the data. The length of each line is equal to the absolute value of the residual for one of the driving assignments. When a residual is squared, the resulting value is equal to the square that is formed using the vertical dashed line representing the residual in the graph that we have on the right, which is one side of a square. Thus, when we find the linear regression model that minimizes the sum of the squared errors for the Butler trucking example, we're going to be positioning the regression line in a manner that's going to minimize the sum of the areas of these 10 squares. So here we have the actual equation where we're looking at the values that are minimized, as well as our y-intercept equation where b naught is equal to the average of my y values minus b1 times the average of my x values.